So, we are now going to speak about limits, the second part of the limits. We had been speaking about its definition in terms of epsilon delta, which is now the standard one, and we had tried to explain to you, maybe it was not very clear, that what would happen if I change the roles of epsilon delta, that is I fix delta and then try to figure out the epsilon. It is not always possible, and we will discuss that more in the notes, rather getting into the details as why such a thing is not possible, that if you say that I will have all those y's such that y is equal to fx such that this happens, then I might not always have x's lying in this. So, this change of epsilon and delta is always not a good idea. So, this definition of a limit is what this means, or rather we want to say that this means this. Once this happens, I will make this notation. Sometimes definitions cannot be questioned, but sometimes what happens, we want to go into the literal meaning, the English meaning of that, and try to see whether it fits in with the mathematical statements. Now, here if you look at the last example where we have taken a function fx equal to 3x and tried to show that, okay, if I know the epsilon, I will find the delta. So, there of course, we were going at x was going towards 5, and at 5 of course, the function was well defined. Now, let us take an example of a function where a very typical function, this is called the topology sine curve, which is given as follows. So, you understand that this function, of course, x is in R, I am not going to write this thing repeatedly. Of course, you know that this function is not defined at x equal to 0, because 1 by x would blow up, and so what would happen now? So, if it is not defined at 0, so what would happen if I take the limit of fx as x tends to 0? This function, if you draw the graph, would look something like this. Maybe I should draw it here. Okay. Now, the function oscillates like this, and as it it oscillates, means it touches this lines y equal to x and y equal to minus x. And it oscillates heavily near 0. Of course, there is a wonderful symmetry of this stuff, and so on. So, this is the graph of x equal to fx equal to x sin x. Sometimes people want to define let x equal to 0 be 0. That is because the limit actually becomes 0. So, at x equal to 0, you want to define this function as 0. So, this limit is actually 0. It looks obvious because, okay, it does not matter, because sin x is always taking value between 1 and minus 1, and so if I take x towards 0, that should just take me to 0, which is some sort of a logic which is alright. But if you want to validate it through its definition, then you would see there is tremendous amount of oscillation of this function. So, how can we really find a delta given an epsilon? But here it turns out that it is very simple, that take any epsilon greater than 0 and I know that this would be strictly less than epsilon. I want to make this strictly less than epsilon, because now I am just looking at this. If it is a limit L is 0, then I am looking at this, which is same as which is less than, now mod sin 1 by x is less than 1. So, I can write this as mod x into mod sin 1 by x, and mod sin 1 by x is less than 1. So, this is less than mod x. Now, because this into this is nothing but mod x into mod sin 1 by x. Mod sin 1 by x is less than equal to 1. So, we will straight away get into this inequality. Now, if I choose mod x to be always less than epsilon, in this case my delta is epsilon. You see the function looks complicated, but your epsilon delta is very simple. So, if I choose this to be less than epsilon, my delta to be less than epsilon, then I get f to be less than epsilon. So, in this case my choice of delta is epsilon. Of course, here when we are writing like this, we are expecting L to be a number, finite number, and A to be a finite number too. But what would happen, because we are already using the term infinite, infinity, what would happen if I write a statement like this? Does this have any meaning? Secondly, also, if I can write a statement like this, does this have any meaning? Now, the second one says that if I make x very large, so in effect here I cannot consider left limit and right limit, I have to consider only the left limit, because there is nothing like right limit for infinity, because there is nothing beyond infinity, right. It simply means that as the value of x becomes larger and larger and larger, the functional value is smaller and smaller and smaller, or the smallest functional value is not smaller, functional value is going towards L, it is stabilizing gradually towards L. For example, if you take a function this is a very famous curve, hyperbola. So, if you take the limit of this function, so my limit symbols could be sometimes lim, could be sometimes LT. It depends on possibly the mood I would have at that moment. That is not a very good thing to do, but that happens. It just mathematicians are sometimes, they just keep on changing symbols, but they mean the same thing. Now, so if if this tends to infinity, if you look at the graph of this, you can understand that this is going towards 0. So, this one, this fx goes to 0. So, what it means? It means that x becomes very large, the function value is going towards 0, function value is becoming very small. So, how do you write this statement, for example, this statement? What is the meaning of this? It says, if I give given epsilon greater than 0, no matter how small, there exists say a real number k element of R such that for all x, this is the symbol of for all, this is a standard mathematical symbol, means for all x which is bigger than or equal to k. So, k could be as large, for every epsilon there would be a k such that for every x which is bigger than or equal to k, this distance would be less than your chosen epsilon. That is the meaning of this. While the other one means, if I look into this, it means here I cannot talk about epsilon because my functional value is going to expand. So, for any So what the idea is that for whatever natural number you take, any n here, so I can always show you a neighborhood around A such that for every x in this A, the functional values of whatever x you take, fx values would always go to this. Yeah, that is the meaning. Sorry, for any any n element of n, there exists a delta greater than 0 such that for all x with f of x must be bigger than your n. So that is the meaning of, so it is a blowing up situation. So however big n you choose, however large this n you choose, it does not matter, it could be 1000, 1000, 2000, 10,000, I can always find x's near A such that the functional values are just going up. For example, if you take the same function 1 by x, and if you look at this thing, limit of fx as x tends to 0. I will just change the function a bit, I will take it 1 by x square. So the value would be positive whether it is on the plus side or minus side. So let me take fx, so suppose I now take fx equal to 1 by x square, then this is also true, and then limit x tends to 0, whether it is coming from the right side or left side, it does not matter. This 1 by x square would start blowing up, the value would be coming. So here you see as you come towards 0, the functional, and if you write 1 by x square, the other part is here, other part of the graph is here. So if you come to 0 from this side also, the functional value, as you come nearer and nearer, the functional value is blowing up. So this is, so these are the various ways a functional value function can approach a limit as x takes various, x goes towards either infinity or towards a finite number. Now is this epsilon delta formulation helpful in telling me some more information about the limit? For example, you would not bother much in the high school level that whether, okay, whether what would happen, will a function have two different limits? It looks intuitively, no, it cannot have two different limits, but how do you prove? Because there are so many functions and uncountably infinite of them, so you cannot check for each and every one that whether it has a single limit or more than one limit. So in that case you really have to base your statement on a proof, and that is why proofs are so important in mathematics. So here we want to say that the limit, so if I say that I have observed this limit fx as x tends to say A is L, then L is unique. Now how do I prove this? The only way it can be proved very easily is using this approach. So this epsilon delta method, instead of getting worried about its writing that, oh, it looks very fearful, I think you should simply go ahead and try to use it. A lot of things in mathematics is done just by using it. Getting used to things in mathematics is very important. So you should just get used in the first case to try to use that and get results rather than bothering exactly about the philosophical issues or what was it, whether it is really a good definition. So we can leave those things to the philosophers and we can really concentrate on the main issue at hand. So what does it mean? Let us take that there are two limits of this. So let L and M be two limits, two different limits, two distinct limits. So the limit goes to L as well as M. Distinct limit means L is not equal to M. So what do I have now? So I will take an epsilon. Once I know epsilon by 2. ठीक है. So now what I do, for any epsilon there exists delta 1 epsilon greater than 0, there exists delta 1 greater than 0 such that whenever x is lying here, I have fx minus L less than epsilon by 2. Right. So, this delta 1 is a delta 1 corresponding to epsilon by 2. Similarly, for the same epsilon, there exists delta 2 such that fx minus m, the other limit, such that whenever x is in this range, this holds. So, you simply blindly applied this definition here. Now, you might say, oh, what am I going to do with this definition? Oh, fine, let us see what we can do. So, we are going to prove that L is equal to M. So, can there be a delta for which both of these definitions, both of these things hold together? It is obvious, because if this works for certain delta and if this works for certain delta 2, and if you take the minimum of both of them, then it will work for this, then that delta would work for this. So, you can choose a delta which is minimum delta 1 and delta 2, means is less than both delta 1 and delta 2. So, then for that delta this will work, because then the x that you choose is both within the delta 2 neighborhood and within the delta 1 neighborhood, right. So, then you can work with both. So, both definitions would work. Now, I will particularly choose epsilon to be L minus M, and this is strictly bigger than 0 because L and M are not same. So, now let me write down. So, now, so for any epsilon greater than 0, there would exist now a common delta which is minimum of this, such that fx minus lambda L should be less than L minus M by 2, because now I have chosen epsilon to be L minus M. So, for that L minus M there is some delta 1. Again, for the next case for M, L minus M is another delta 2. So, again I take the minimum and it works for both. Now, what I would do is I will come into a contradiction very simple way. So, this I will write as and this is a well known result that mod of A plus B is mod A plus mod B. Now, here I have chosen particularly epsilon equal to L minus M. So, I know that for all x, so for all x with this delta, so now for every x with x lying between delta plus A and delta A plus delta and A minus delta, with this particular delta, I would have this to be less than epsilon by 2 and this to be less than epsilon by 2, but for this particular choice so which means this is strictly less than L minus M. Now, somebody might suddenly get confused that I have suddenly chosen epsilon is equal to L minus M. Observe the very statement here, given any epsilon, if you want to be more precise, I should write here given any. So, given any epsilon, whatever be my epsilon, I do not care, as long as it is greater than 0, no matter how small, there would always exist a delta 1. So, if I put epsilon as mod of L minus M, there exists a delta 1 for which this will happen with L minus, here I will replace this by L minus M by 2. The same thing will happen here if I put epsilon equal to mod L minus m, there will be a delta 2. Now the delta that will work for both of them would be the common delta, the minimum of delta 1 and delta 2, and for all such x's this is true. So, what I am finally getting that L minus m is strictly less than L minus m, which is a contradiction, and hence my original assumption that L is not equal to m is wrong. So, this proof is a proof by contradiction. It is one of the greatest tools in the hands of a mathematician. We have already used this proof by contradiction, especially in the Cantor's diagonal method. The proof by contradiction is a key thing. That is the, you take something, take the wrong take the thing which is opposite of the conclusion and show that there will be a contradiction. Now, this is one method of proof, and people might say, okay, oh, this is for mathematics, I do not care, if you just give me the information, that is fine. But let me tell you, in mathematics just having an information does not make you have a true knowledge about mathematics, because mathematics is all about structures, it is not just about numbers. So, here what you see is the structure of mathematics, how a mathematician thinks, how a proof has a logical validity, because unless you demonstrate that okay, if you say, oh, I can really drive my car at 200 kilometers per hour, then you should really demonstrate that you can drive at 200 kilometers per hour. You cannot just say, and you can't just say that, oh, I can drive at 200 kilometers per hour and everybody should believe it. So, a mathematical statement, if I say, oh, the limits must be unique, it is like a statement same as I can drive at 200 kilometers per hour. The question is, why should you believe me? The only thing, if you believe me, because I can make a demonstration that what I am telling is true. So, this mathematical demonstration is just like any other demonstration in life. So, if you want to be a school teacher, for example, you need to give explanation when your interview comes. You have to teach things so that people know whether you are a good teacher. Even you go for an interview process for a job, why you have an interview? Because you have to demonstrate your capability. So, demonstrating anything, when you make a statement that I am this or I am that or this happens, then it is very important to demonstrate. If you can't demonstrate, that does not make any sense. So, in mathematics, the demonstration, the methodology of demonstration is done by the rules of logic, and this is the way one does it. I do not think it's, once you start getting habituated to it, it makes so much of a problem. It just, you will see the use of this rule again. I will use a result which you know very well, and which you might think, okay, this is very fine, very simple result, why unnecessarily make my life unhappy by trying to prove this. So, there might be questions by some students that, okay, why are you trying to touch the nose in a roundabout way? For example, this statement, I think everybody knows it. Assuming that all of you are largely from the undergraduate first year students. So, what do you mean by this? What is happening? So, first of all, I say, oh, limit of the sum is sum of the limits. Oh, we know this from our high secondary days, we have been doing all these things. But for a mathematician, such an answer is not acceptable. So, there is this famous story of an astronomer, a physicist and a mathematician, and were roaming in the Scottish Highlands, and they saw some ship far away, which was black possibly. So, the astronomer said, oh, all ships in Scotland are black, and the physicist says, now come on, you cannot make such a sweeping generalization. You can say black ships are found in Scotland. Then of course, they turn to that Wardi, the mathematician. Mathematician say, sorry, I disagree with you both. To me, the animal over there, because it was slightly far off, so it was not exactly clear whether it was a sheep or not, but it appeared more or less like a sheep. but to a mathematician look at the rigor. He says that the animal over there appears to be black on the side facing us. So, if I am going to really look into this formula, the first step of rigor as a mathematician would be to define what I mean by this new function f plus g. It is like a summing up two machines. I tried to explain to you functions as some sort of a machine, and so here we are summing up two machines. So, what do you mean by this summing up? So, if now it operates on input, what does it say? So, we have to first define that this is same as first operating f and g individually and then adding the outputs. That is the meaning. So, this is the definition of the function f plus g in terms of the function f and g which are already defined. Once you do that, you can define this. Now, this is only true if the limit of g and limit of f exists. Now, if limit of fx extends to a is L and limit of gx extends to a is m, then it is, you would know that of course. See, here the interesting factor is that we are not sure whether the limit would exist or not, because this right limit left limit issue is there. So, in this case, if you just know that the limit of these two exists separately, then the limit of this exists and it is L plus m. Now, limit might not always exist. For example, I have quite often seen in standard local calculus books, they write a statement like this. But this is grossly wrong, because this limit does not exist as x tends to 0, because when you go, if you look at the graph of the parabola, see, that is why it is very important that you draw graphs of functions. You should actually sit down, maybe with computers now, with mathematical softwares, try to look at the graph of the functions which will tell you the real nature of the function. So, when x goes towards 0, the function value blows up towards plus infinity when it is coming from the right side, but when it goes from the left side for the function f(x) equal to 1 by x, it goes down to minus infinity. So, the two limits left and right are not same, so you cannot write such statements. So, limit does not exist in that case. In a theoretical sense, we often admit limits as plus infinity. Here it means it does not matter which way I am going towards a, like x square. So, it is tending to 0, I will have this. So, when you have f(x) equal to x square, you just have to flip this graph, because it will always not take the positive value. So, it will be a symmetric flipping, it will be a mirror image, and then your limit would exist. So, this example is a good example of the trick. Now, you might ask, so how do you prove this? You would say, oh, what is there to prove? Nothing, there is nothing to prove. But no, this needs a proof. How do you? Because if you can show that L plus m is the limit of this, then you are actually proving two things in one goal, that you are proving that the limit also exists, because you are concretely showing that it is L plus m. So, that is the thing. So, mathematical rigor is not just a cup of tea which you might just not want. It is a cup of Karela juice, possibly you have to drink for many. But it is fun. Once you start, you are being able to do proofs. It is just a matter of time for those who have little bit of liking for mathematics would start liking it. Of course, there will be this cross fight between algebra and analysis. Analysis would be more hand waving to many people who like algebra, but a very famous economist recently told me that when he was when he learned mathematics at his undergraduate level, he always thought that algebra was the king, he solved one of the most famous books in algebra by Herstein at his undergrad level completely, and analysis was all topsy-turvy. But later, while he was doing research as an economist, he found that this approximations etc. in analysis was the key to everything. The analysis is largely about change. In this calculus is about change and is about approximations. How well we can record a change. That's the whole thing. Now, for example, if I have to prove this, so I have to prove this thing. So, take epsilon greater than 0, right. Second, what would happen? So, there would exist delta 1 greater than 0 such that oh, I forgot to write. I am so habituated doing all these things that it skips my mind. Similarly, there would exist delta 2 such that whenever x is here, now I can use a common delta. Now I can use the so if I take the minimum of delta 1 and delta 2, both these would hold at the same time. So now you have a very simple job left to do. It's just basically some algebraic manipulation. So now we have x minus x, when x is lying between a plus delta and a minus delta, where delta is this one. So for all such delta a's, by all such x's, let us see what happens. So given the epsilon, is this delta the corresponding delta for this? So you just fx put with, so you use this definition f plus fx plus gx, and then make fx minus l plus gx minus m, and then use mod of a plus b is less than mod a plus mod b. So now for all x with delta, where delta is the minimum of delta 1, delta 2, I know that this is strictly less than epsilon by 2, this is strictly less than epsilon by 2. So I will have f plus g x minus l plus m is strictly less than epsilon. So whatever epsilon I choose, this is my delta for which this is happening. So L plus m is the limit of f plus g, if L and m are the individual limits. Now you might be wondering that you are showing the existence of limits and etc. by calculating epsilon and deltas. What about showing the non-existence of limits using epsilon and deltas? So with that, with such an example, I will end today's discussion. I am not going to work with this sort of Yale Hospital's rule etc. at this moment, that I will not doing those, I will not doing this kid stuff of doing calculating limits and doing examples, very basic examples. See, as I have already told in the introduction, this is calculus for people who are genuinely interested to learn the structure of the result and not just giving very particular examples. Some particular examples would be given in several cases, but not that every time you just give someone to particular example which will be coming in your examination possibly. And please understand that these courses are not just to make you effective for an examination and then you forget it. These courses are for you to remember them, because you can see them whenever you want. Now, let me take a function which is a very famous function in mathematics called the Dirichlet function, after the famous German mathematician Gustav Dirichlet. If x is rational, so x is in Q is equal to 0 if x is irrational. What should be the limit? This function does not have any limit, because if you take any rational number, say I take x to be a rational number, and I say there is say a, take a and a to be a rational number, and now if x is approaching a from both sides, now among these x's there will be there will be rationals as well as irrationals. So at the rational points it will take, so what is happening is that I can now just think of taking only the rational numbers. So then my value would be 1, but if I take a value from this side, just take the irrational numbers, that also coincides to a, then the value would be 0. But if I take only the rational numbers, then it will be 1. Now, but here I have to move x as near to a. So I take any limit as L. I take L as a limit, right? Some L. Now, what I want to say is that you cannot reach any limit here, because if you look at if you just think about it intuitively, this is just oscillating very fast, 0, 1, because there are infinite, in fact countable rationals and then uncountable irrationals. So they are oscillating 1, 0, 1, 0, 1, 0. So it is very difficult to say you can imagine in your mind that obviously it is not going towards any limit. Now how would you handle that scenario? So can I for example, if I take epsilon equal to 1 by 4th, and say L is the limit, some limit L, suppose it has a limit, and given this epsilon, I should be able to find a delta such that this should happen. Now, however small I make that delta, it does not matter, whatever small I make that delta, mod L would be less than 1/4. So for some x it will be 0. So your mod L, because some x's would be 0. So for whatever delta, however small I take, it does not matter. Suppose I find some delta, then for which there will be some irrationals, for all those irrational points, any irrational point will immediately give you this, if this is true. But there will be some rationals also giving you these two quantities. Do you think these two quantities are possible at the same time? These two are not possible at the same time. So because, so here is L, assume L is positive just for the moment, here is 0, here is 1. So what is happening? So L is less than 1/4, so means L has to be here. So 1 minus L is this part, so it has to be bigger than 3/4. This is 1/4, so 1 minus L has to be 3/4 or bigger. So how can 1 minus L be strictly less than 1/4? So immediately there is a contradiction. Hence, you see I cannot find, it does not matter what delta I take, these equations will always be there. So, I cannot, so I am using the epsilon delta thing to show that given, give me any, I have given you an epsilon and I have taken an epsilon and I cannot find a corresponding delta for which this will hold, because that is leading to a contradiction. So, with this I end my talk on limits, and we are going to talk about continuity and few hard results about the behavior of continuous functions, the intermediate value theorems, and those will come in the next classes. So, tomorrow's lecture would be on continuous functions. Thank you very much.